Hello everyone, I am Mr. P. Mabu Hussain, Assistant Professor of EEE, Institute of Aeronautical Engineering, Hyderabad. So in this video, we are going to discuss about the internal and external flux linkages of an isolated single current carrying conductor. So this topic comes under the module 1, which is transmission line parameters. So here in this module, we already completed in previous videos that the types of conductors, calculation of resistance, factors affecting the resistance of solid conductors, skin effect and proximity effect. So these first 3 topics were completed in the last video. So now in this video we are going to discuss about the only the internal and external flux linkages of an isolated current carrying conductor. So before going to discuss about that, so you need to recall some of the basic fundamentals of an inductance. Right, the voltage induced in an inductor is given by the expression. So E is equal to d phi by dt. Now here phi represents the flux linkages of conductors and the units for this flux linkages is Weber turns. Now this first equation so can be written as d phi by di into di by dt. Right, here in the first equation we are dividing and multiplying with di by di, so this expression can be written as this expression E is equal to d phi by di into di by dt. So now the term d phi by di, you can write it as the inductance L here, right? So L here is the d phi by di. So the inductance, so which is represented in henries. The unit for inductance is henries. Now if you are in a linear magnetic circuit, the flux linkages vary linearly with the current, so such that the inductance remains always constant and is given by the expression L is equal to phi by I, right? So here phi represents the flux linkages and I represents the current flowing through the conductor. Now from this expression, phi or flux linkages can be written as L into I. So this is the expression we must remember for getting the inductance equation for a single conductor or a single phase line or 3-phase line. So we have to remember this equation. Now if the current is of alternating, so then the above equation, so which is this equation, so for psi is equal to Li, this can be written as, so lambda is equal to L into I. Now here lambda represents the flux linkages of a conductor which is carrying a AC current, so which is in terms of RMS value, and I is the current flowing through the conductor, so which is also RMS value. And also you need to recall one important equation that is the Ambience Law. Okay, so this Ambience Law which relates the magnetic field intensity H with the current enclosed by the conductor or path, right? So this according to the Ambience Law, so closed interval of H dl will be equal to current enclosed I enclosed, right? And the flux density, so if you see the flux density which is represented with B, so it is given by B is equal to mu H, and the value of mu here is the mu naught into mu R, and here mu naught represents the permeability of the free space and is equal to 4 pi into 10 to the power of -7, and this mu naught will not have any units, and mu R is the relative permeability of conductor material, right? By which material your conductor is manufactured. So the permeability of that conductor material will be represented with this mu R, and the unit for mu R is henries per meter. So the mu, so which is the product of mu naught and mu R, so which is called the permeability. So the unit for this permeability is also henries per meter. So these are the fundamentals which you must remember to solve or to develop the expressions for inductance of a single isolated current carrying conductor. So now proceed with the calculation of inductance of a single isolated current carrying conductor. Okay. As you know, the transmission lines are composed of number of parallel conductors, and those conductors will be of infinitely very long. You don't know how much distance those transmission lines are going, so that is distance you can assume it to be infinity. Now if you want to determine the inductance for such type of transmission line, first you need to develop the expressions for flux linkages. As you know before, so the flux, the inductance L depends upon flux linkages phi. Right? If you know the flux linkages and current flowing through your conductor, you can determine the inductance. So from this expression, for determining inductance of any conductor, first you need to develop the expression for flux linkages. Okay. So now here we are going to develop the expression for inductance of single isolated current carrying conductor. So for determining the inductance here also, we need to first develop the flux linkages, okay, of an isolated current carrying cylindrical conductor, and the written part here we are assuming to be at infinity. Right? We are going to consider only one conductor, and this conductor is carrying a current I. Okay. So whenever this conductor carries the current according to fundamentals of magnetism, so the current carrying conductor will produce the magnetic flux. Right? So around this magnetic flux, you will be so around this conductor which is carrying the current, you will be having the magnetic flux, and the direction of magnetic flux will be given by the right hand thumb rule. So if you see the second figure here, so if you hold your current carrying conductor in your right hand, so the curled fingers, these curled fingers will represent the direction of the magnetic field if thumb is the direction of your current. Okay, so you have to hold your conductor such that your thumb, right hand thumb will be pointing towards the direction of current. In such a case, curled fingers will represent the direction of magnetic field. Okay, so and here you will be having two types of fluxes. So one is internal flux and another one is external flux. Right? What is internal flux and what is external flux? So internal flux is simply nothing but it is the flux which is inside the conductor. Okay, once the conductor is carrying the current, it will produce the flux. Right? So that flux will be some flux will be internal to the conductor, some flux will be external to the conductor. Okay, so if you take if you observe this figure here, so some flux lines are inside the conductor, right? So always this flux will be represented with concentric lines here. Okay, so the flux which is internal to the conductor, it is called the internal flux. Now after the conductor also you are having some flux lines. Okay, so those flux lines are also concentric circles only. So the flux which is external to the conductor, it is called the external flux. Okay, so while determining the flux linkages, you have to consider both this internal flux as well as the external flux. Okay, so now to calculate the inductance of a conductor, it is necessary to consider the internal flux as well as the external flux. So this division is helpful as the internal flux links a smaller amount of current as we proceed towards the center of the conductor, and external flux always links the total current inside the conductor. Right? So you see, if you observe the figures here, okay, so the first figure, it is the single solid conductor which is carrying the current I, let us assume. Okay, so now whenever this single solid conductor carries the current I, it produces the magnetic flux, and that flux will be either internal flux or external flux. Okay, so both internal flux and external flux will be there if you carry the current. Now if you see only the internal flux, right, which are the fluxes inside the conductor. Okay, so the flux inside the conductor is called the internal flux. Now if you observe this internal flux will links only the smaller amount of current. Okay, so if you pass the current through this conductor, so this current will be uniformly distributed across the conductor. Okay, so uniformly distributed across the conductor if you neglect the skin effect. Okay, if you take the skin effect, the current will take outer layer of the conductor. So here we are going to neglect the skin effect. Right, when you neglect the skin effect, the current distribution will be uniform inside the conductor. Okay, now if you observe the internal fluxes, now these internal flux will links only the smaller amount of current. Okay, so but if you see the external flux here, that this external flux is linking the total current which is flowing inside the conductor. Suppose if you take from center of the conductor to a point x, so a point P which is at a distance x meters. Now if you consider the internal flux inside this, okay, so this internal flux inside this area will links only the current which is distributed in that particular area only. Okay, so this flux doesn't link with the current flowing here outside this area, right? So if here to here also you have the current distribution will be there, current distribution will be there. So but the flux what we consider which is inside this part, so that current that flux internal flux will not links with this current, so here to here. So always if you see the internal flux will links only smaller amount of current. Okay, but if you see the external flux here is outside the conductor, right? So now this external flux will links the entire current which is flowing in the conductor. Okay, so always remember these 2 points. The internal flux links the smaller amount of current, while the external flux links the total current which is flowing inside the conductor. Now let us develop the flux linkages of single conductor due to only the internal flux. You consider only the internal flux and you develop the expression for flux linkages of a single conductor. Okay, so for that you consider a cross-sectional view of a long cylindrical conductor which is carrying the current I, which is shown in figure here. Okay, this figure shows the cross-sectional view of long cylindrical current conductor, so which is carrying the current I. Now according to Ambience law, if you remember or recall the Ambience law, so the MMF, magnetomotive force, which is called the MMF. The MMF around a concentric closed path of radius x, right? If you see this concentric closed path of radius x which is internal to the conductor, so the Ambience law expression will be in closed interval of h x dl will be equal to I enclosed in that path. So that means we are considering only up to a distance x here, this area. Okay, so what is the current enclosed by this area is Ix. Okay, so if you take the MMF around a closed path, so which is having the total area of your conductor, so then that Hx will be, so that according to Ambience law, integral of Hx dl will be equal to total current I you will get. Okay, so now as you are considering only up to the radius of x, so here the current will be Ix. Okay, so now since the field, the magnetic field is symmetrical, this Hx is always constant at all the points which are equidistant from the center of the conductor. Okay, so now, so the first expression, in the first expression, as Hx is constant at all the points which are equidistant from the center of the conductor, so you can take it outside, right? So this equation you can write it as Hx into closed interval of dl into, so dl is equal to Ix. Okay, so now what is this integral of dl? Okay, so if you consider this concentric circle, okay, so this total length, right? So integral of dl is nothing but total length of the path, right? So total length from if you see here, as this is a circle, so the total length of the circle, if you see, it will be equal to perimeter. Okay, so which is having the radius x here. Okay, so this can be the perimeter, you can represent as 2 pi r here. So but the r here is the x only, so you can write it as 2 pi x. So this expression can be written as Hx into 2 pi x is equal to Ix, or you can write it as 2 pi x into Hx will be equal to Ix. Okay, as I said before, I am neglecting the skin effect. Okay, I am also assuming the uniform current distribution inside the conductor, right? So when you assume the uniform current distribution inside the conductor, which is nothing but, so if you take the current density, okay, so this current density is always same. Okay, current density is same inside the conductor. If you take this conductor, one conductor here, okay, the current density at any point if you take, so the current density will be constant or same if the current is uniformly distributed across the conductor. How we can express this current density? So current density rho will be equal to current per unit area. So current per unit area. Suppose from the center of the conductor, if you take a conductor which is having a radius x, so then the current density for this path will be equal to current enclosed by that path, which is Ix, by area of that will be equal to pi x square. Okay, now if you consider the total conductor, then current density rho is equal to total current I by area is pi r square. Okay, so now the current density will be same here. This current density and this current density both are the same. So in such a case, what you can write, Ix by pi x square will be equal to I by pi r square. So both will be the same. Okay, so now from this you can write Ix will be equal to pi x square by pi r square into I. Now here pi and pi will get cancelled. So Ix can be written as x square by r square into current I. So let it be equation number 3. Okay, so now from equation 2 and from equation 3, so now you are going to write another expression. So that means here we are going to substitute equation 3 in equation 2. So in such a case, what you get, 2 pi x into 2 pi x hx is equal to this value. Okay, 2 pi x hx is equal to x square by r square into I. So instead of Ix, we are writing this expression, x square by r square into I. So equation 2 can be written as 2 pi x into hx is equal to x square by r square into I. Now from this expression, the only hx value is equal to Ix by 2 pi r square you will get. Okay, so hx is the magnetic flux intensity. Okay, flux intensity, and this units will be ampere turns per meter. Okay, so now let it be equation number 4 here. Okay, so once you know the magnetic flux intensity, you can determine the magnetic flux density. Okay, so magnetic flux density B is equal to mu h. Once you know the intensity, okay, we are using this expression to calculate the magnetic flux density up to a distance x from the center of the conductor. Okay, so magnetic flux density at a distance x meters from the center of the conductor can be written as Bx is equal to mu into hx. Okay, so this you can write it right here. Mu x, this can even be written as mu naught mu r into hx. Okay, so now we are going to consider to be equal to 1, so that Bx will be equal to mu 0 into hx. Okay, now the value of hx is Ix by 2 pi r square from equation 4. So that equation 4 we are going to substitute in equation 5, so that you will get Bx is equal to mu 0 I by 2 pi r square into x. Okay, so here the value of mu is always equal to mu 0 into mu r, which is called the permeability of the conductor. Okay, so now let us consider an infinitely small tubular element which is having the thickness dx and length of the conductor to be 1 meter. Okay, so here you consider this length of the conductor will be 1 meter. Okay, so in this you consider only small tubular element here, so which is represented as dx. Okay, so you consider the infinitely small tubular element which is represented as dx for a long conductor which is having a length 1 meter only. Okay, so now if you see the flux inside this tubular element, okay, the flux inside the tubular element can be written as d phi. So that d phi will be equal to b into area of the area. Okay, so bx we can say. Okay, so phi x, so d phi x is equal to bx into a here. Now a is the area. Okay, so length into distance you can say, right? That area can be written as dx for 1 meter. You are taking 1 here, and distance is at a distance dx. Okay, so this length, if you see, so this is dx, and we are considering the 1 meter length conductor. So dx into 1 will be the length of this tubular element. Okay, so the flux in the tubular element, if you want to determine, so that will be represented with d phi x, and this value will be equal to flux density bx into area, and that area is the area of your tubular element. So area of tubular element will be equal to, so this distance of your tubular dx into length we are considering to be 1 meter, so you are keeping it to be 1 meter. So d phi x will be equal to mu 0 I by 2 pi r square into x dx, right? So from bx we already derived, so that value is mu 0 I by 2 pi r square into x. So from this you can write d phi x will be equal to mu 0 I by 2 pi r square into x into this dx. Okay, let it be equation number 3. Okay, now the flux dx, which is the flux inside the tubular element, right? So the flux inside the tubular element, this flux dx will links only the small amount of current, so which is inside this tubular element only. Okay, so the flux d phi x will links only the small amount of current which is inside this tubular element. Okay, so therefore on assumption of uniform current density, so the fractional turn, so which is pi x square by pi r square of the total current will be linked with this flux. Okay, so then d lambda x, so the flux linkages. Okay, so flux linkages lambda will be equal to flux into tons. So this will be represented with Weber tons. Okay, so flux linkages will be equal to flux into tons. Okay, so flux is in Webers, tons will be tons. Okay, the unit for flux linkages will be Weber tons. Okay, now if you determine the flux linkages from this flux d phi x, so which is linking a number of terms which is equal to pi x square by pi r square. So in such a case, the d lambda x, so which is the flux linkages inside this tubular element will be equal to x square by r square into d phi x. Okay, so flux is d phi x and tons are this one x square by r square. Okay, you have to consider this. Okay, so then d lambda x will be equal to so from this expression mu 0 I by 2 pi r power 4 into x cubed you will get, right? So from this, in place of d phi x you can substitute this, right? So I erase this. Okay, in place of this d phi x, so if you substitute this expression here, so you will get d lambda x will be equal to mu 0 I by 2 pi r power 4 into x cubed dx. Okay, so let it be equation number 7. Okay, so this d phi x, d lambda x, this d lambda x is the flux linkages. So flux linkages inside the tubular element. Okay, so flux linkages inside the tubular element. Now if you want the total flux linkages inside the conductor, so then how you can determine? You have to integrate this d lambda x from center of the conductor, so which is at a 0 distance, to up to the radius. Okay, if you integrate this expression from 0 to r, you will get the total flux linkages inside the conductor, so which is called the internal flux linkages. Okay, so internal flux linkages now will be equal to lambda internal, so this value will be equal to integrating this d lambda x from 0 to r. Okay, so d lambda x you have to integrate with respect to dx. Okay, so now what is this d lambda x? The d lambda x is mu 0 I by 2 pi r power 4 into x cubed dx. Okay, so the lambda internal will be equal to integral 0 to r mu 0 I by 2 pi r power 4 into x cubed dx. Here you will get. Okay, so now you solve this expression. Okay, so here mu 0 I by 2 pi r power 4 into I. So this total expression, you can take it out. Okay, I'm writing here. Okay, so from this expression, you can write it as integral. So this expression is equal to, so here mu 0 I by 2 pi r power 4. This total value is constant. You take it out, mu 0 I by 2 pi r power 4. So integral of 0 to r x cubed dx you will get. Okay, so from this expression, you can write mu 0 I by 2 pi r power 4. So now integral of x cubed will be x power 4 by 4. So and limits are from 0 to r. Okay, so now this you can write it as mu 0 I by 2 pi r power 4 into, so if you take r, you will get r power 4 by 4 minus 0 you will get. Okay, from this you can write it as mu 0 I by 2 pi r power 4 into r power 4 by 4. Okay, so now here r power 4 will get cancelled. So you will get mu 0 I by 8 pi. Okay, so the internal flux linkages lambda internal will be equal to mu 0 I by 8 pi. Okay, so the flux linkages units will be Weber turns per meter, as you know already. Okay, now here what is the mu naught? Mu naught is the permeability of free space, and this mu naught value will be equal to 4 into 10 to the power of minus 7. Okay, so if you substitute 4 into 10 to the power of minus 7 in place of this mu 0, then lambda internal you can write it as 4 pi into 10 to the power of minus 7 by 8 pi into I. Okay, so now here 4 pi here you can multiply with 2. Okay, so for pi will get cancelled, 4 2s I will get. So the lambda internal or internal flux linkages will be equal to 1 by 2 into 10 to the power of minus 7 into I, Weber turns per meter. Okay, so this is the expression for total internal flux linkages for a single conductor carrying the current I. Okay, so once you know the flux linkages, you can determine the inductance. Okay, now calculate the inductance of the single conductor by considering only the internal flux. Okay, so the internal flux linkages you know, right? So the internal flux linkages of conductor due to internal flux is lambda internal is equal to 1 by 2 into 10 to the power of minus 7 into I. So the inductance due to internal flux alone will be L is equal to, so the flux linkages, internal flux linkages by total current I. Okay, so this will be the internal inductance. Okay, as you are calculating this inductance with only internal flux, you can call this inductance as a internal inductance, L int. Okay, so this L internal inductance will be equal to lambda int by I. Now here lambda int is the this value, so which is equal to 1 by 2 into 10 to the power of minus 7 into I by I. So this I and I will get cancelled. So lambda internal will be equal to 1 by 2 into 10 to the power of minus 7. Okay, you have to remember this. So lambda internal will be equal to 1 by 2 into 10 to the power of minus 7. And the inductance unit you already know, which are henries. Okay, so now this lambda internal will be equal to 1 by 2 into 10 to the power of minus 7 henries per meter. So per meter, why we are taking here? We are considering only the 1 meter length of the conductor. Okay, so because of that reason only, this expression will be henries per meter. Okay, this is how you can calculate the internal inductance and internal flux linkages. Now let us see the flux linkages of a conductor due to the external flux. Now you have to consider the external flux alone, and you have to calculate the total flux linkages. Okay, so for that we are going to consider a point P, so which is at a distance d meters from the center of the conductor. Okay, up to which the external flux is distributed. Okay, so as you already know, whenever the current whenever the conductor carries the current, it produces the magnetic flux around it, right? So now this magnetic flux will be both internal as well as external. Now here we are going to consider only the external flux. External flux in the sense the flux which is distributed outside the conductor. Okay, so now here the flux distributed outside the conductor will be up to what distance? So up to what distance? We don't know. So because of that reason, we are going to consider a distance d meters from the center of the conductor, and up to that distance d meters, we are going to find out the total external flux linkages. Okay. So here we are going to consider a point P here, a point P, so which is at a distance d meters from the center of the conductor. Now we are going to calculate the total flux linkages from the surface of the conductor and to that point P, okay, around this conductor. So for this also you have to consider the tubular element dx. Okay, so here also we are going to consider the tubular element dx. Okay, so inside this tubular element then we will calculate the d phi x, right? So which is the flux. Okay, flux inside the tubular element. Then from the flux you will determine the flux linkages. So once you know the flux linkages, you can determine the inductance also. Okay. Now since the magnetic flux lines are concentric circles around the conductor, whole of the flux which is between the surface of your conductor and the point P, so it will lies within the concentric cylinder surface which is passing through that point. Okay, so the magnetic flux intensity, so which is at a distance x meters, we already derived, right? So that will be equal to hx is equal to I by 2 pi x. Okay, so this is already derived while discussing the flux linkages due to internal flux alone. Okay, we are directly taking that expression here. So hx is equal to I by 2 pi x. So this is the magnetic field intensity at a distance x meters, so from the center of the conductor. Once you know the flux intensity or field intensity, you can determine the bx value. Okay, magnetic flux density. So bx is equal to mu 0 into hx. Okay, mu 0 into hx you can take. So bx is equal to mu 0 into, in place of hx you can substitute I by 2 pi x. So bx will be equal to mu 0 into I by 2 pi x you will get. Okay, so let it be equation number 11. Now, so the flux outside the conductors, if you observe, so this flux outside the link, outside the conductor links total current which is flowing inside the conductor, right? As this total flow, as it is linking the total current flowing inside the conductor, the flux linkages d lambda x manually, so numerically it will be equal to d phi x. Okay, so this d phi x and d lambda x both will be same. Why? Because this total flux outside the conductor links with the entire current flowing inside the conductor. So d lambda x will be same as the d phi x. Now the d phi x value you already determined. This value will equal to bx into dx into 1. So 1 here represents the 1 meter length of the conductor. We are considering 1 meter length of the conductor, and dx is the length of the tubular element. Okay, and bx is the flux density. Okay, now from this expression of bx you already know. So bx is nothing but mu 0 I by 2 pi x, that you are going to substitute here. So then this d lambda x will be equal to mu 0 I by 2 pi x into dx you will get. Okay, so d lambda x, so this is the flux linkages inside the tubular element here. So inside this tubular element, if you see the total flux linkages, so that value is represented with d lambda x. Okay, so d lambda x will be equal to mu 0 I by 2 pi x into dx, and this units are Weber turns. Okay, so here it is represented wrongly. So as it is a flux linkages, the units are Weber turns. Okay, so now after knowing the flux linkages inside the tubular element, okay, you can determine the total flux linkages from surface of the conductor to a point P which is at a distance d meters. Okay, so from this point surface of the conductor to point P, so from here to here you have to determine the total flux linkages. How you can determine? So by integrating this d lambda x from surface of the conductor which is at a distance r from the center of the conductor to capital D up to a point P which is at a distance d meters. Okay, so when you do this, you will get the total flux linkages external to the conductor, so which is called the external flux lambda external. Okay, so lambda external is equal to integral of r to d. In place of d lambda x, you have to substitute this expression, mu 0 I by 2 pi x into dx. Now here from this expression, so mu 0 I by 2 pi, so this is a constant, you can write it outside, mu 0 I by 2 pi integral of r to d 1 by x dx you will get. Okay, so now from this you can write mu 0 I by 2 pi, so integral of 1 by x, this will be equal to ln x, so and limits are r to d. Okay, so now this can be written as mu 0 I by 2 pi ln d minus ln r. Okay, so now this ln d minus ln r, you can write it as ln d by r. Okay, so the final expression lambda external, so lambda external will be is equal to mu 0 I by 2 pi ln d by r. Okay, so these are Weber turns per meter. Okay, so Weber turns per 1 meter. Okay, as we are considering the 1 meter length of the conductor, so the units are Weber turns per meter. Okay, right, you have to remember this. Okay, so this represents the total flux linkages outside the conductor if the current is if the current flowing inside the conductor is I. Okay, right, so once you know the total flux linkages outside the conductor, you can calculate the inductance due to that flux linkages. Okay, so total flux linkages external to the conductor lambda ext will be written as mu 0 I by 2 pi into ln d by r Weber turns per meter. Now from this flux linkages you can determine the external inductance, which will be equal to external flux linkages by current flowing inside the conductor, right? So lambda external here is mu 0 I by 2 pi into ln d by r here, okay, by I. So this I and I will get cancelled, so that this external inductance Lext will be equal to mu 0 by 2 pi into ln d by r you will get. Okay, and the units for inductance will be henries per meter, as we are considering only 1 meter length of the conductor, so units you can write it here as a henries per meter. Okay, as you know, this mu 0 is nothing but 4 pi into 10 to the power of minus 7. Okay, now you can do the calculations here, pi will get cancelled, 2 2 you will get, so this expression 13 you can write it as 2 into 10 power minus 7 ln d by r. So this is the external inductance. Okay, external inductance is equal to 2 into 10 to the power of minus 7 ln d by r. Okay, so now you calculated flux linkages which are internal to the conductor, then inductance for inductance due to internal flux. So after that you calculated the total flux linkages outside the conductor and you calculate the inductance also. Okay, so then what about the total flux linkages? Okay, if you take a conductor and if you pass the current through the conductor, so it produces the magnetic flux. Now this magnetic flux lines will link with the will link with this conductor, and total flux linkages of this conductor due to this internal flux as well as external flux, if you both consider, so then the total flux linkages will be equal to lambda, so which is equal to lambda internal plus lambda external, right? So we developed the expression for lambda internal and lambda external, and the lambda internal will be equal to 1 by 2 into 10 to the power of minus 7 into I, and the lambda external is the 2 into 10 power minus 7 into I ln d by r. Okay, so see here, so from this expression, okay, if you substitute here 2 pi into 10 power minus 7, so then 4 pi into 10 power minus 7, then this can be written as 2 into 10 power minus 7 ln d by r. So this is the, so in here you also get the I. So lambda external is equal to 2 into 10 power minus 7 I into ln d by r. So that you are going to substitute here. Okay, so now in the both the terms we are going to take the common 2 into 10 power minus 7 into I. Okay, so 2 into 10 power minus 7 I, if you take common from the both the terms here, okay, then in the first term you can write 1 by 4, and the second term you will be having this term ln d by r. Okay, so now this 1 by 4 you can write it as ln e power 1 by 4. So why? Because ln e power anything will be equal to somewhere x. Okay, so now if you know the value of x, so this you can write it as ln e power x. That I am going to do here. So 1 by 4 I am writing it to be ln e power 1 by 4. Now this will be log a plus log b. So it can be written as ln e power 1 by 4 into d by r you will write. Okay, so from this again you can write it as d by, so this e power 1 by 4 it is passing to denominator, so then you can write it as ln d by r into e power minus 1 by 4. Okay, so now this can be written as 2 into 10 power minus 7 I ln d by r dash. Okay, here r dash represents the r into e power minus 1 by 4. Okay, if you solve this you will get 0.7788 times r. Okay, the value of r dash here will be equal to 0.7788 times r. So you have to remember this. Okay, so this is called the geometric mean radius for a single isolated conductor. Okay, so now here equation 15 represents the total flux linkages of a current carrying conductor, single isolated current carrying conductor which is carrying current I. Okay, so then once you know the total flux linkages, you can determine the total inductance of a conductor. Okay, so the total inductance of single isolated conductor due to both internal flux as well as external flux up to a distance d meters from the center of the conductor, it will be given as L is equal to lambda by I. And here the lambda is nothing but 2 into 10 power minus 7 into I. So this lambda is 2 into 10 power minus 7 into I ln d by r dash. So which is from expression 50. Okay, so by I you will get, right, this I and this y will get cancelled. So the inductance expression will be equal to 2 into 10 power minus 7 ln d by r dash, and the units are in henries per meter. Okay, so now if you want to convert this henries per meter into millihenries per kilometer, how you can write? Okay, or if you want to convert this ln term to logarithmic term. Okay, so ln term, if you convert this into ln term, how you can write? So we will see here. Okay, right, now this expression you can write it as L is equal to 2 into 10 power minus 7 ln, so this ln is nothing but log d by r dash to the base e here. Okay, so this can be written as 2 into 10 to the power of minus 7. So this ln d by r dash to the base e, you can write it as ln d by r dash to the base 10 multiplied by log 10 to the base e. Okay, right, now the value of 2 into 10 power minus 7 log 10 to the base e multiplied by log d by r dash to the base 10. Okay, now so this will be in henries per meter. Okay, so now if you want to convert this into millihenries per kilometer, okay, so that means this henries per meter, if you want to convert into millihenries per kilometer, what you need to do? You have to multiply this with 1000 and again 1000. Okay, so I will write this again. So henries per meter, you can write it as 1000 millihenry. 1 henry is equal to 1000 millihenry. 1 meter is equal to 1 by 1000 kilometers. Okay, so from this henries per meter will be equal to 10 to the power of 6 millihenries per kilometer. Okay, so now if you want to convert henries per meter to millihenries per kilometer, you have to multiply that henries per meter into 10 power 6. Okay, so now if you write this again expression, 2 into 10 power minus 7 log 10 to the base e multiplied by log d by r dash to the base 10. Now in place of henries per meter, you can write 10 to the power of 6 millihenries per kilometer. Okay, now if you solve this, 10 power 6 into 2 into 10 power minus 7 log 10 to the base e, you will get the value as equal to 0.4605. Okay, so now the inductance L will be given as 0.4605 into log d by r dash to the base 10. So units are in millihenries per kilometer. Okay, so you can remember either this equation or you can remember this equation also. Okay, so this equation is easy to remember, 2 into 10 power minus 7 log d by r dash. Okay, you remember this expression so that we can solve some numerical problems later. Okay, so thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.